Okay, good morning. I'm Gurva Sofia, and I'm going to present my work on branched flow. Well, the phenomenon we investigated is connected with the propagation of waves through a weak disordered potential, and waves start forming channels or branches of high intensity, and they keep dividing on the wave's further path. It's quite a general phenomena for waves of different wavelengths. And in 2001, it was discovered for electrons on two-dimensional electron gases. Well, in semiconductors, the electrons from a point-point contact were expected to form smoothly spreading fans, but with the use of scanning probe microscope technique based on position conductivity measurements, it was possible to visualize the flow, and it appeared that that electrons form branches. As I mentioned, the appearance of the effect is connected with the presence of weak disordered potential, and in this work, the researchers explained the presence of such potential by the donor dopant atoms and unwanted impurities in the sample. And I already said that the appearance of the phenomenon is connected with the present is quite universal, and it also can be observed in optics. And the observation of this effect in optics is more affordable and it requires less sophisticated equipment. So we investigated the propagation of a beam in glycerol water subfilm. Well, it can be shown that both electrons' wave function and the electric field component of the optical wave satisfy the second-order differential equations of the same kind. For electrons, it's time-independent Schrödinger equation, and for the electric field component, it's Helmholtz equation. And in case of electrons, we mentioned that the potential is created by dopant atoms and impurities. And what about the film? So if we use the model of a slab guide, we can express the deceleration rate of the wave, or it can be thought of the effective refractive index. From the dispersion relation for a slab waveguide, we can express it as a function of the thickness of the film, and as there are variations of thickness in real SERP film, these variations act as this weak disordered potential. From mathematical statistics, it can be shown that there are features of the flow that do not depend on the kind of correlation function in our potential, but only on some global parameters, the correlation length and potential strength. The distance of the first branching is it can be shown that it has the following dependence on the correlation length and potential strength, and this formula is quite intuitive because correlation length is kind of a scale on which the variation in potential occurs, and and we can expect that first perturbation of the wave can appear on the same scale, and As for the potential strength, the weaker the potential, the longer it takes it to affect the initial flow. So the distance of the first branching is expanding. So we move on to the experimental part of our work. As an input wave, we used two lasers of different power and wavelength. We used water soap and glycerol solution film stretched inside the photometric cuvette, and observations were carried with the use of microlens and video camera. Firstly, on this slide, I show how the beam propagates through a volume filled with the solution. It experiences simple diffraction broadening, and these are the this is the beam inside the film. The branches of high intensity we described are quite visible, and here are more results for the green light, and we also had the hypothesis that the effect can be observed inside a transparent tape. So we put the laser to the transparent tape. In previous works, the observations were only carried on the soap films, and we obtained these results, but we cannot definitely say whether it is real branching. I also tried to qualitatively investigate the potential in the film, and on the right you can see a sample photo of our film in cuvette, and on the left there is a probability density function of the grayscale image, and it shows that the distribution of the of great color on the pictures is close to normal, and in our further work we are going to make an interferometer to measure the thickness of the film, and as in fact the color reflected from the film is connected to the film's thickness, the image shows that the distribution of the potential is close to Gaussian. So in our work we obtained photo and video materials for branched flow phenomenon demonstration in optics in order to illustrate this phenomenon that we firstly found in electrons flow, and that was firstly found in electrons flow. We carried kind of qualitative investigation of the background potential. The distance of the first branching in our experiments is of the order of 1 millimeter, which is in correspondence with the article we based our work on. And we have a plan for the future investigation and development of the report. So if I have some time, these are more results we had, and this is propagation of this is branching in a curved film. You also can see the videos on the disk, and see that the effect has kind of time evolution.